OK, so 3.6. So just a reminder, we're winding down the third epoch of the course, also the third chapter of the book, which is all sorts of shortcuts. So quick algebraic ways, important things to know, just kind of so you can do calculus, use it. And we've got a bunch of shortcuts already. They're festooned over the board over there is festooned with them. And today we're going to use the chain rule to figure out a few new shortcuts. So let's see. Where do I want to begin? Where are my notes? Here. And in particular, we'll use the chain rule and inverse functions to come up with some formulas. So let me do 2 examples, and we'll get a nice a couple new formulas, and then you'll get to practice those, and we'll start at it. All right. So this is 3.6. So here's an example. So we're going to let f of x equal x to the half. And we're not going to get a new rule out of this, but you'll see a clever way of using the chain rule to reaffirm something we've already known. So if I square both sides, I would get that. And now I'm going to take the derivative of both sides of this equation, and something neat will happen. All right. So I do this. Oops. All right. So on the left-hand side, we'll have to use a chain rule. But hopefully you're pretty good friends with the chain rule by now. So this is the derivative of blah squared. What's the derivative of blah squared? 2 blah. So this thing in square brackets I'm calling blah. That's the inner function. Then I need to multiply that by the derivative of the inner function. And the derivative of the inner function is just, well, the derivative of f. So I'm sort of pretending I don't know what the derivative of the inner function is. And I'm saying, I don't know, it's just f. So the derivative of the inner function is f prime. And the derivative of x is 1. Yep. So now let's solve for f prime of x. You don't look impressed. So what we've done is we've said, all right, I don't know. Suppose we don't know the derivative of a function. But I do have some sort of relationship like this. Right? So these two relations are inverses, square rooting and squaring. So I can write down an equation like this. Take the derivative of both sides, use a chain rule on the left, solve for the derivative, and I would come up with that. And that's just what you would get with a power rule. OK, you still don't look impressed. But that's your right. So again, we haven't really gotten anything new, but this is just showing that this is all this is consistent. And what we're going to next do is use this method for a function whose derivative we don't know, and then we'll figure out something new, and maybe you'll look more impressed. Or, or not. Again, it's up to you. All right. All right. So let's see. I'm going to, so here's another example, I guess. E to the log x, what does that equal? X, yeah. So I'm going to play the same game. I'm going to take the derivative of both sides. Derivative of e to the log x. All right, so let's do the left-hand side first. That's where we encounter our friend the chain rule. So log is the inner function. E is the outer function. So we're going to call log blah for a moment. The derivative of e to the blah is? E to the blah, excellent. And then I've got to take the derivative of blah. But we actually don't know what that is. And the derivative of x is 1. Excellent. OK. E to the log x is still x. Ta-da. OK, good. One person is impressed. I'll take it. I'm not going to push my luck. So what we've done now is we've figured out the derivative of the natural log using this trick. And that was something we didn't have a shortcut for before. So we can add that to our list of rules. And so now we have a new rule, and we can take all sorts of derivatives of logs now, and we can use the product rule and the chain rule with logs. And now here's your chance to do that. So let's do problem 1, but skip problem F. So let me just say a few things about these and see if they're questions. So log 3 is just a number. It doesn't depend on x at all, so its derivative is 0. How does log 3 depend on x? It doesn't. Log 3x, this is a chain rule problem. So 3x is the inner function, so we'll call it blah. So the derivative of log blah is 1 over blah. That's our new rule. And then we need to take the derivative of the inner function. The inner function is 3x. The derivative of 3x is 3. So the 3's cancel, and we get 1 over x. Same story here. Derivative of log whatever is 1 over whatever. Then I need to take the derivative of the inner function. That's going to be 12x squared. This one is product rule and a chain rule. So I take the derivative of the first one, leave the second one alone, plus leave the first one alone, take the derivative of the second one. And it's easy to forget that there's also a chain rule going on here as well. So this 3x is an inner function. It doesn't look as obviously functional as this does. This sort of screams out chain rule to you. This is a little more subtle. It's easy to forget that these 3's and 2's end up making a difference. So the derivative of sine blah is cosine blah. And then this 3, because the derivative of 3x is 3. I leave log alone, plus leave sine alone. Derivative of log 2x is 1 over 2x. Then the derivative of the inner function 2x, the derivative of 2x is 2. Questions so far? OK. Let's do this one. So this is a triple chain rule. So first we've got the derivative of sine of whatever, and that's just cosine of whatever. and whatever is this now. Then I need to take the derivative of whatever, the derivative of the inner function. That's log 3x, which actually it turns out that we've already done. So the derivative of log blah is 1 over blah. Then the derivative of 3x, the innermost function, is 3. So this whole thing, well, the 3's cancel and we get 1 over x. You could also refer back to this problem.
With that one, like, when you get the, like, you start with the other one, that makes sense. But like, when you get to the natural log of 3x, wouldn't you just get the derivative of that, which is 1 over x, and then get the derivative of 3x, which is 3? So,
but the derivative of,
like, wouldn't you end up doing the derivative of 3x twice?
No, I mean, because once you, so this is, this piece here is that. And so the derivative of log blah.
OK, but you don't have to find the derivative of the blah of log.
You do eventually. That's the last. That's what this last 3 is.
OK.
So the derivative of log of, maybe it would be.
But no, isn't the derivative of 3x 1 over x? Because you have to do the chain rule for that, so you get a 3 also that you then.
No, I think, I mean, so the derivative of log of this is 1 over 3x. And then you do take the derivative of 3x, and that's what this 3 is. So maybe, let me, at the risk of complicating matters, that's probably never something you want to hear a math person say, but I'm sorry. So the function was this. Then that would be cosine log x cubed. Let me write that down here so I can fit it in one line. Cosine log x cubed. Then I need to take the derivative of the inner function. Derivative of log whatever is 1 over whatever. And then I need to take the derivative of the innermost function, which would be 3x squared. So maybe this was a little potentially confusing because this is such a, it's barely a function. I mean, that's a judgment. I mean, who am I to say? But it almost looks like x. It's not. If you have something that looks like a more complicated inner function, maybe it's easier to see the mechanics of the chain rule. All right, so let's try problem number 2. And you can tell this. So I teach this class every other year. So the last time I taught this class was during the presidential election cycle. So you can probably guess what happened the night before if you maybe remember this debate. As I do, I saw this when I was looking at my notes last time and started chuckling to myself. Anyway, give number 2 a try. There's a point to this exercise in addition to reminiscing about Mitt Romney that you'll get to in part C. Anyway, so have some fun with this, and it actually will lead to an interesting mathematical conclusion. All right, so here's the function. And to get its rate of change, we take the derivative. That's what the derivative tells us, the rate of change. And so this is sort of one of these hidden chain rule things. It's not an obvious chain rule, maybe. Derivative of e to the blah is e to the blah. Then I need to take the derivative of blah, the inner function, 0.15t. Its derivative is 0.15. So there we got the derivative. Then we need to just plug in t equals 5, and we can get these numbers. What are the units on this one, by the way? Tweet. This would just be tweets. This one is going to be tweets per hour. All right, so then if we want the percent growth rate, so I want to know this many tweets per hour is what fraction of the current number of tweets. Right, so So I'm going to take 317.6 over 2117. And did anybody do that? Yeah. OK, so I took the, so this is the growth rate. And I want to express the growth rate not in terms of number of tweets per hour, but as the fraction of the current number of tweets. What this is saying is that that growth rate is 15%. And you could even say this is 15% per hour. Well, oh, to turn it into a percent, yeah. Sorry, let me, so this is tweets. What's it? This is tweets. So 15 per hour, or 15% per hour. So this is, months ago when the course first started, we talked about continuous growth rates for exponentials. And you all said, why is it continuous? And I said, I'll tell you later. And you maybe have forgot about that because there's so many other things that happen in between. Anyway, we're going, now that we know the chain rule, we can sort of explain that. So if you've got a function, well, you can kind of see it. If you didn't, I don't want to do this. So we've got a function like this. So this is what we basically just did with 1,000 and 0.15. So then the percent growth rate is just f prime over f, which is all this stuff. If we used some other base, we used an a here, we'll have that annoying log a, and we couldn't make that statement. So this is just to justify why, when we have exponential growth in this form, we call this the instantaneous growth rate, or continuous growth rate. So at any given instant, it's growing at 15% per hour. All right. You look similarly unimpressed at how you did at the beginning of class. But again, that's your prerogative. But at least now I've made good in the promise to go back and talk more about why that's the continuous growth rate. All right, so last thing, let's try problem 3. This is a little bit of a review of signs and a little bit of a review of a problem on the midterm that a couple people got a little turned around on. So let's give this a try, and then we'll wrap things up. So let me, sorry. So let me go over this. There are a number of places to go wrong on a calculator when you're entering this in. And maybe this is fresh in my mind because I looked at 38 of these problems over the last couple of days. But anyway, a lot of people got confused on different aspects of this, so that's why and it was a log problem on the test. This is a sign problem, but why I thought it'd be worth going through it. So difference quotients, it's just change in f over h. And so f of x is sine 3x. F of 4 plus h, you replace x with 4 plus h, and 3 multiplies all of x. So the 3 has to multiply the 4 and the h. And then at this point, it's basically calculator time. There's not much you can do with it. I mean, you could write this as 12 plus 3h. This is 12. On the midterm, a lot of people did not entirely legal things with logs. So you can't you can't pull this apart in any way. So even if you wish it were the case that this was true, right, so you can't separate sine like that. You can't separate logs like that. I think sometimes there are these nice log properties that sometimes make things simple, but then people think that you can just simplify log any old which way. Anyway, so that was a mistake, understandable, that a lot of folks made. So when I did this on a calculator, I ended up with this and then this. And another issue that I think came up for some people, when you're entering this, you need to put parentheses around everything upstairs. Otherwise, because you want to divide everything upstairs by h, not just the second term by h. So I think that was something that a couple people did as well. So I ended up with 2.73 and then 2.56. And then I decided that was enough. I didn't want to keep going with smaller and smaller h's. If we use the shortcut, this also makes you appreciate the shortcut, doesn't it? Yeah. OK, so that's good. We can end on an appreciative note for shortcuts. It's one of these slightly undercover chain rule. Remember, the 3 gets kicked out front. So 3 cosine, 3 times 4. And oh, I did this on my calculator. I didn't write it down. 2.532. So I was headed in that direction. All right, the last thing that I want to mention. So I went through, at the beginning of class, and I think the verdict was this was moderately impressive, a derivation of the derivative of the natural log. And it's a nice answer. It's 1 over x. So logs are nice functions in that way. You can play similar games with other functions. If you had a different base log, you would end up with this. Inverse trig functions, I don't think we're going to do a lot with them. But for the sake of completeness, I feel like I ought to at least write them on the board. They're in your book. You might need to use these formulas once or twice in the homework. Again, they don't come up, in my experience, these things don't come up that often. But it's useful to know that there are indeed formulas and nice shortcuts for them as well. So next class will be the last of Epoch 3. A few more sort of loose ends from the chain rule and things like that. And then we'll be ready to start applying the derivative in different settings week 8, 9, and 10.
Well, it's a fan inside of here, this board.
Natural log of 10, yep. So that's it for today. I'm happy to stick around and answer questions or do anything.